So on number 9, from our worksheets. For section 6.2. And we have cosecant squared of theta, 2 theta that is. And then cotangent 2 theta, d theta. Alright, so ultimately we need to look and see if there's something we substitute here that would ultimately give us a means to get rid of both of these parts, if you will. And keep in mind, we always want to look for something that we could, if we let something equal u, we're going to have to let something equal, or we're going to have a du that's going to have to hopefully be related to the other stuff that we want to get rid of, if you will. And in this case, isn't the, if we let our u be cotangent 2 theta, wouldn't du be negative 2 cosecant squared 2 theta? D theta? Ultimately, the derivative of tangent is secant squared, the derivative of cotangent is negative cosecant squared. And ultimately, we have to use the chain rule when we do the du on that because we have a 2 theta argument instead of a theta argument. Right. So ultimately, with that, if I write my integral, then I could write this part as u. Again, the cotangent 2 theta part becomes u. And then what I have left is I have that stuff and that stuff together. And ultimately, I have almost that here in this sentence. But I'd have to divide by negative 2 here, get negative half du equals cosecant squared 2 theta, d theta. And then ultimately I would have that negative half du equal exactly what I have left. True? So therefore I could put my negative 1/2 out in front. And then my du here. And if I anti-differentiate, I get u squared over 2 plus c. And resubstituting, I'd get negative, and then in parentheses, cotangent 2 theta squared all over 4 plus c. Assuming I left it in that form. All right. Questions? All right. What else? 18. We have sine radical x and radical x on the bottom. Dx. We have a definite integral here. Pi squared over 4, pi squared. Alright, so, and they told us what to use for the substitution here, and if we do that, we'd get radical x, and our du here would be 1 over 2 radical x dx. And again, some of these simple functions that we continue to have to find derivatives for, hopefully we just know that at this point. If you don't know that, you don't have that memorized, you'd have to write x to the 1/2 and get 1/2 x to the negative 1/2, which ultimately will give you 1 over 2 radical x. So, like I said, for time's sake, and I would start memorizing these functions that appear quite often, just so you don't have to waste the time of having to figure that out. Just know it. So, with that, we have if we let our integral here be sine u, then. And ultimately we have a 1 over radical x dx here to get rid of. Well, we have almost that here. We just need that 2 to be out of there. If we multiplied both sides by 2, we'd have 2 du equals 1 over radical x dx. And therefore the other stuff, the radical x on the bottom and the dx, that's exactly what we have right here. We can replace that with 2 du. So with that said, if we do our antiderivative, it would be negative cosine u. Negative 2 cosine u. The antiderivative of sine, negative cosine. And remember, we're evaluating that on blank to blank because we have u values here. And then if we resubstitute our radical x in there, so our pi squared over 4 and our pi squared here. Alright, and if we put our pi squared in there, we're going to get negative 2 cosine pi minus negative 2 cosine pi over 2. So ultimately we're taking the square root of those two arguments. And cosine of pi we know is negative 1, so that ultimately would be 2 right there. Cosine of pi over 2 is 0, so ultimately we get 2 minus 0, which is 2.
Does that say pi squared on the sheet?
This is pi squared over 4 and then pi squared.
Okay.
So pi squared is the upper limit, pi squared over 4 is the lower limit. Questions on that one? Another? None? 27, we got 6x cubed on top, and we got 4th root of 1 plus x to the 4th on the bottom. Alright, so with that one, they don't tell us what to substitute this time, so we need to come up with something here. Something would tell me that this is probably what we want to substitute, since if we anti-differentiate, or if we differentiate it, we'd get a cubic, which we have a cubic on top to get rid of. So if I let my u equal 1 plus x to the 4th, my du would be 4x cubed dx, which would be related to 6x cubed dx, is what we have on top. So when we substitute, and we're going to get our 4th root of u on the bottom, which is just a power function, so that's fine. Problem is, though, how do we get rid of 6x cubed dx when we have 4x cubed dx? Well, ultimately we want this side to read 6x cubed dx. True? So what could we multiply 4 by to get to 6? 1.5. So 3 halves du then would be 6x cubed dx. We need that sentence to read 6x cubed dx because we want to replace it with something that it's equal to. And so ultimately that would be 3 halves du. 3 halves times both sides would give me what I need here on top. So that means I'll have 3 halves here and du here. And then antiderivative here, keep in mind that the integrand here is u to the negative 1/4. So if we anti-differentiate that, we're going to add 1 to it, and we're going to get u to the 3/4 divided by 3/4. Keep in mind there's a 3 halves out in front of all this. And then from there, if we simplify, we get 4. Our argument here, 1 plus x to the 4th over 3 to the 3/4. Keep in mind again, there's still a 3 halves out in front. So 3's would cancel out, 4's and 2's would cancel out. You get 2 and then 1 plus x to the 4th to the 3/4. That plus what? And I'll do it. Questions on that one?
When you put u in, why is it just 1 over the 4th square du? What happened to 6x to the 3rd on top?
The 6x to the 3rd dx got replaced by 3 halves du.
Oh, okay.
So ultimately we're replacing that stuff with u. And then we also have this stuff to get rid of, the 6x cubed dx. Okay. That's why we wrote this sentence right here, so we could get rid of this stuff and bring in this.
Okay.
Okay. So that right there is equal to 3 halves du. So there's our 3 halves, and our du replaced the 6x cubed in the dx. What else? Another one from this group? Mike? 48. Let's see, 48. We have a definite integral. 0 to 1, it's like 0 to 1. We have y cubed plus 6y squared minus 12y plus 5 times y squared plus 4y minus 4 dy. And it ultimately it says just evaluate here, so we really have a couple of options here. If we wanted to, we could certainly just we could multiply all that out and get one big polynomial and then just use the power rule for each of the terms. That's one option. Let's try and see what happens if we substitute though, and see if that might be better or quicker. It may or may not be, but we'll try it. So if we did that, our du here would be 3y squared plus 12y minus 12 dy. And ultimately, if I do my integral here, I'm going to have u here, and then ultimately I have this and this to get rid of. And if you look at this stuff right here, if I were to factor a 3 out of that, wouldn't I have exactly that quantity? And so therefore, 1/3 du, if I divide it by 3, I would have exactly what I want, y squared plus 4y minus 4 dy. And therefore I could replace 1/3 here and du here, and then anti-differentiate. So if it's a definite integral, put it in a box, put our dashes on there. So I'll have 1/3 here, and then our y cubed plus 6y squared minus 12y plus 5 all squared over 2. And now we can put in our 0 and our 1. And conveniently for us, the 0 and 1 are pretty easy to put into this polynomial. So if we put in a 1, let's say we get 1 plus 6, that's 7. And then minus 12. 7 minus 12 would be negative 5. Negative 5 plus 5 would be 0. So ultimately 1 gives us 0. So we'd have 1/3, we have a 0 minus. And then on this side, a 0 in here would give us 5. So we'd have 5 halves. So if we did the math on that, negative 5/6. Negative 5 halves times 1/3. Okay.
Just as I'm down. So when you find u, and then you take the derivative of it, and that's du.
Yep.
And then you want du to equal what's left of your integrand.
Yeah, anything that's not substituted by u, then hopefully the other stuff should be related to du somehow.
Okay. That's why you want to get that out. And then
So ultimately you need to get rid of everything that has a y in it, including the dy, and bring in stuff that is related to u, or du. Alright, again, could we have gotten to that by just multiplying this out originally? If we just did the multiplication on that, we'd have a whole lot of terms, but ultimately we could just do that and then just do we wouldn't need substitution, would we? So, again, one way is not necessarily better than the other. This is probably a little bit quicker, maybe not much quicker though. Right?
You have like 5 halves, but you're supposed to like square what you put in the top, like so it's 0 in the top.
Oh, you're right. Sorry. So this should be squared then, shouldn't it? The 5 should be squared at least.
Yeah, 5 is squared,
So
so
it'll be 25/6 then. 25/6. There we go. I forgot about the little square there. We read my own writing. So 0 ultimately is still 0, but in the 5 on top should have been 25 halves. So 25 halves times a third would be 25/6. So there we go. Others? On 51, we have a differential equation, ds dt, and the differential equation is 24t and then 3t squared minus 1 cubed. All right. And it's also an initial value problem. They give us the s is 0 when t is 0. So ultimately, if we do our separation of variables here, we're going to get 24t and then 3t squared minus 1 cubed dt. And if you notice, there is no s terms at all, so therefore this really is separation of variables, but we don't really need to. This is one of the simpler kinds because there's no s part here. So if we anti-differentiate both sides, we get s on this side, which is convenient. And then on this side, we have a choice again. We could either multiply all this out and have a power function, or we could use substitution here. If we use substitution, our u would be 3t squared minus 1. Du would be then 6t dt. And keep in mind that that would get rid of that part. But we have 24t dt. Well, here we have 6t dt. So if we did 4 du, that would give us 24t dt if we multiplied both sides by 4, wouldn't it? So that means in our integral then we're now looking at 4 out here and then u cubed du here. So again, the u is replacing the 3t squared minus 1. The 24 dt is replaced by 4 du. And then our antiderivative then would be u to the 4th over 4 plus c times 4, keep in mind. So ultimately just be u to the 4th plus c. Not over anything, I guess. So just u to the 4th plus c. So that means on this side I'm going to have 3t squared minus 1 to the 4th plus c. So ultimately, again, the key issue here is separating the variables and then anti-differentiate both sides, whatever technique we need to anti-differentiate we can use. And then from there, our initial condition is 0, 0. So if we put a 0 in here and a 0 in here, we're going to get negative 1 to the 4th plus c. So we'd have 0 equals 1 plus c, so negative 1 would equal rc. And so the final answer then would be s equals 3t squared minus 1 raised to the 4th minus 1. Questions on that one? What else? Josh? 54, another differential equation, so this time it's ds dt equals negative 4, nope, that's the second derivative one. So we got negative 4 sine 2t minus pi over 2, and that's it, right? Alright, so they ultimately if we're going to solve this we have to do essentially what we did here before twice, because we have to anti-differentiate just to get back to our differential equation here instead of our second derivative equation here. So we ultimately have that as our separated variables here, and ultimately to anti-differentiate both sides we'd get back to ds on this side and then anti-differentiating here. And keep in mind that what we find here is ultimately going to be the derivative when we do the final part here, so we can write this as ds for the time being, but it's really a ds dt when we get done, because when we integrate here we're going to wind up with something dt. Okay. So in terms of integrating here, if we did our u substitution, we'll do the integration over here, we'd get negative 4, I'd take that out, we got sine here, we got 2t minus pi over 2 dt. If we u substitute that, we get du equals 2 dt, so we get half du equals dt, and therefore we could take the half out in front and get negative 2 out in front. We have sine of u du, and then if we anti-differentiate here we're going to get negative cosine, so ultimately it would be 2 cosine u, which u is 2t minus pi over 2 plus c. Now, one might ask here is if I just knowing that I really have something of the form of sine kx, and I know the antiderivative is 1 over k sine k or cosine kx, negative 1 over k cosine kx. I mean, ultimately, is the negative 1/2 doing anything for us here in terms of the chain rule? I mean, if that negative 1/2 wasn't there, ultimately it would just be sine kx, wouldn't it? So we might say, do I actually have to write all this down, or could I just go right straight to the answer? I mean, it depends on how well you can visualize, I guess. I mean, you know, I've done it enough where I wouldn't need to write all that down. I could just, you know, go right to the answer from that. But like I said, it's best case is use the substitution. That way, it's pretty tough to go wrong if you follow the steps correctly. So bottom line here is that we have our ds equals 2 cosine 2t minus pi over 2 dt, and I'm going to put the dt back over here. Keep in mind that we have plus c here on the end of it because we anti-differentiated, and they gave us the initial condition that the derivative is equal to 100 when time is 0, or t is 0. It's necessarily a time or not. Alright, so let's see what happens here. We got 100 here. Cosine of negative pi over 2 is negative 1. So we'd have negative 2 plus c here. Be 102 then equals c. And therefore our differential equation now reads 2 cosine 2t minus pi over 2 plus 102. Alright, questions on part 1 so far? And ultimately, what are we going to do with that now? Same thing, we're just going to start over with that same equation. So if we, we'll bring it over to another sheet at this point. If our ds dt, would separate our variables, 2 cosine 2t minus pi over 2 dt, and then integrate again. Now we get to our s. And once again, same argument here. We could do the use substitution here, and if you want to write all that down, you may, but I'm just going to, for simplicity's sake, I'm going to just go to the answer here, which is 2t minus pi over 2 plus c. And if you don't believe me, differentiate this. If I differentiated this, wouldn't it be cosine of this argument times the derivative of the argument? Which ultimately would be 2 cosine of the same argument. Okay. And then our initial condition for the s is our 0, 0. So if we put a 0 in here, and we put a 0 in here, we would get, actually did I, you know what? Gosh, that's stupid. That's dumb. Hold on. Let's go back to this. I think I was thinking backwards on this. Going back to this, cosine of negative pi over 2, that's 0. Yeah, that whole thing is 0. So ultimately this is 0 plus c, so it'll just be 100, not 102. And then over here, I didn't keep my 100 in here, so plus 100 dt. So there's our whole integrand. And so ultimately I need 100 t here then, plus c. So we have that 100 as part of our integrand. Yep, so we're anti-differentiating this, so we get that part for that part. Antiderivative of 100 would be 100t plus c. Now if I put my 0 in there, this is actually going to be 0 anyway, I guess, for that part. But now the sign of negative pi over 2, that is negative 1 plus c. And so therefore we get 1 equals c for the c part of that. So again, we're putting a 0 in here, we get sine of negative pi over 2. Sine of negative pi over 2 is negative 1. So sine of 0, we're at 0. Going backwards would be down negative 1. 100 times 0 would be 0, of course. So we end up with negative 1 plus c, which c equals 1. And then our final answer then would be sine of 2t minus pi over 2 plus 100t plus 1. Alright, we got it straight this time. Any questions on second part? And ultimately, are the first and second parts really any different than one another? So ultimately, to get from the second derivative to the function, now we just have to do it twice. We gotta anti-differentiate, figure out what c is based on the initial condition for the derivative, and then just do it again and then figure out what c is based on the initial condition for the function. What else? Devin? 42, we have a definite integral that is 2 radical y here, and then 1 plus radical y to the second. dy on top, which I generally always write it like that instead of having dy on top, put it on the side. And with that, if we substitute 1 plus radical y, okay, I would pick that out immediately because I know the derivative of that would be 1 over 2 radical y, and isn't that related to what I have in my other part right here? So that means my substituted integral then becomes, actually this is definite, so what is it, 1 to 4? Alright, my substituted integral then would be u squared here. And again, the 2 radical y on the bottom that we have here and the dy here, that's exactly what we have right here in du, isn't it? So that means that right there and that right there are gone, and we just put in du. So ultimately, what do we have left? Just u squared on the bottom, and that's it. So if we anti-differentiate, u to the negative 2 would be u to the negative 1 over negative 1. And if I put back my numbers in here, it'll ultimately look like that then, wouldn't it? U to the negative 1 would make it go down on the bottom. Divided by negative 1 just makes the whole thing negative, so just put the negative 1 on top, put the argument down on the bottom. And if I put in my 4 here, I'm going to get negative 1 over 3. Put a 4 into that. Negative 1/3. I put a 4 in there and then minus. And if I put a 1 in there, I'm going to get negative 1/2. And if I add those two, negative 1/3 as a 6, bottom would be negative 2/6 plus 3/6, which ultimately give me 1/6. And that'll do it. Alright, let's move to the practice quiz next then, and come back to it if we have time. here since I have slope field to be drawn here. Number 1 is B. 2, the solution to the differential equation is x cubed minus 2x plus 1. And drawing that slope field, again just going through each of those whole number points and drawing those segments. Should look something like that. And then again, when we overlay the solution, we need to make sure that number 1 happens that it goes through the point -1, 2. Because they gave us that as the initial condition. So if our curve we draw doesn't go through -1, 2, then that's going to not be correct. And then ultimately from -1, 2, we just roughly draw along that slope field. We also have a pretty good idea of what this picture should look like since we know that y is equal to it's a cubic. So when we draw, we should draw a cubic. If we do something different than a cubic, that wouldn't really make much sense. But so ultimately that should be our picture there. And then parts or number 3 and 4 are both C. Okay, questions? Anything on that part? Yep.
Do number 2.
Okay. So similar to what we just did with the other differential equations here. If we have dy dx equals 3x squared minus 2 and we move our dx and then we anti-differentiate both sides, we get y equals, and then over here we get x cubed minus 2x plus c. And the initial condition again was -1, 2. So if we put a 2 in and a -1 in, we get -1 plus 2 plus c. That'd be 1 plus c. Subtract, we'd get 1 equals c. So again, we're just putting those numbers in there, -1 and 2, and solving for c. So if we do that, that's our c, and that means our final answer then is x cubed minus 2x plus 1. And then again, for the slope field part, when we do our slope field, and we can start with x equals 0, if you will, keeping in mind that this is only based on x here, so that means that when we put in 0 into the equation for x, we should get 0 minus 2, which is -2. So again, all along here, we're just going to draw slopes of -2. So all those would have slopes -2, those segments. And then if we go over here to 1, our 1 in there would give us 1. So we'd have a positive slope here, positive, positive. And again, all these we'll draw as such. If we put a 2 in there, we'd have 12 minus 2, we'd have 10. So at 2, we got something very steep. And as we go to the right, it's going to get even steeper yet. Put -1 in there, we're going to get 1. So -1, all our slopes are 1s. And if we put -2 in there, we're going to get -10, which again are going to be very steep here again. So again, you can draw however many of those they ask you for. But again, key element here is that we have -1, 2 as our point. So when we plug in that -1, 2, we make a point at -1, 2. And then again, the general shape here, we can see is, it's going up on the left side of this here. And as we go here, we're going down and then back what? And back up. So a simple sketch might look something like that. Questions on that one?
If you're drawing a sketch of that, and you're putting like the actual line through it, do y values matter, like where you put it? Or?
Well, yeah, because they gave you -1, 2. You got to make sure it goes through the initial condition.
Okay.
So that's how you find it. If the initial condition was -1, -2, we would have made a point here, and then our picture would have been down below. So, what else? And 4, they give us substituting 0 to pi over 3, cosine to the 4th, x sine x dx. And here, substitution-wise, if we differentiate sine, we're certainly not going to get cosine to the 4th, so it probably wouldn't make sense to call sine our u. But if we let cosine be our u, then our du would be negative sine x dx. And so therefore, my substituted integral would look like u to the 4th here. And my negative sine x dx, I have that right here, except for it's positive. So if I just make it negative du equals sine x dx, I can replace that whole thing with negative du. So ultimately then, our integral would look like that then, wouldn't it? I replace cosine x with u, that would mean u to the 4th. sine x dx is equal to negative du. So if I can get those out of there and put in du and negative. Anti-differentiate, I get u to the 5th over 5. And then if I plug back my cosine x in there, 0 and pi over 3. So that would be the setup. And then if we use the fundamental theorem, we're going to get opposite of cosine of pi over 3, we know is a half. A half to the 5th would be 1/32. And 1/32 divided by 5 would be 156. What's that? 160. Thanks. Times 2 times 5 is 10, not 6. Thank you. So I'd have 160 here, right? Because again, this is a half. Half to the 5th would be 1/32. 1/32 times 1/5 would be 1/160th. And then if I put a 0 in there, cosine of 0 we know is 1, so we'd have 1/5. Right? And then from there, if we do the subtraction here, if I multiply 160, 1/160th minus 1/60th here, multiplying 5 into 160, 5 would go into 160 32 times. We just did that a minute ago. Right? So ultimately it would have the opposite of that. And so it would be the opposite of negative 31 over 160. So it would be 31 over 160. And ultimately, if they tell you to use substitution to calculate this, then this is the work that you need to show, of course. However, since it's a definite integral, and if this is on the calculator portion, is there a way to check it? Couldn't this just be done with the calculator in the first place? Then do math rack and make sure it gives you 31 over 160.
Right, is that the after sort of it?
Yes.
Yeah, math 9.
Math 9. What else? Done?
So on a cosine x does to the 5th power, do you do cosine x divided by 5 then go to the 5th power? Or
No, definitely not. You got to follow the order of operations. So power first, and then divide by 5. So that's why we got 1/2 raised to the 5th is 1/32,
Oh, okay.
and then 1/32 times 1/5 instead of divide by 5 times by 1/5. Good questions. What else? Anything else from our review assignments, worksheets?